So good afternoon, everybody. It's nice to see we have a good turnout, even though it's Sunday and it's cold. As you know, this is the first one of two review sessions covering what the department feels are the most important, most fundamental chapters in for Finance 3000 courses. And today I will cover Chapter 5, Time Value of Money, and Chapter 6, which is the chapter on bonds. Your final is cumulative, as you know. What? You don't hear me? No? You can't hear me. So I'll just speak louder. I don't know. I don't think this is actually connected to the speakers. It's only for you, right? Okay. I'll try to speak louder. Remind me if you can't hear me. So your final is cumulative, and I taught this class for I think 3 or 4 semesters. I'm not teaching this semester, and but the experience of most professors teaching this is that when people early in the semester have trouble with Chapter 5, and they kind of have a blurry understanding of the concepts in time value of money, then it's very hard for them to recover. Like, it's a very important chapter because it really teaches you some fundamental concepts that you need for bonds and you will need for stocks later in the semester. So it's very important that now you get it. And also Chapter 6 tends to be confusing, so we will focus very much on these 2 chapters today. If you have questions about something else at the end, maybe I can answer them also. But really try to get these 2 chapters very well now, so that when you will be studying for your final, which is cumulative, you have a lot of stuff. You are not going back trying to understand what present value is, because at that point it will be too late. So time value of money shouldn't be a very confusing chapter, because it really just gives mathematical structure to something that you all have an intuition even before stepping inside a Finance 3000 class. It's just telling you money received or paid at different points in time is not the same. And I said everybody has a very clear intuition of this, because if a friend of yours asks to borrow money from you, it's you feel very differently if she says, I'm going to pay you back tomorrow, or I'm going to pay you back in 30 years. It's the same, maybe the same cash flow, but receiving back that money at a very distant point in time in the future feels very different. So time value of money actually tells you how you can compare cash flows being paid or received at very different points in time. So you should never compare cash flows occurring at different times without first discounting them to a common date. And present values let you do just that. Lets you take a cash flow in the future and discount it back maybe to now. One type of exercise that we'll see, I think it's maybe the first of the second in this list of exercises that you received, lets you also understand how much cash now you should set aside if you have some future outflow that you are anticipating. Meaning, in a year I want to buy a motorcycle, I know it costs $5,000, but in the meanwhile I can receive some interest if I have money now. How much money should I have now so that in a year I will be able to afford the $5,000 motorcycle? This long sentence basically can be converted to what is the present value of $5,000 in a year. Okay? So let's see. What else do we have? So before we step forward, it must be very clear to you what these 2 concepts are, present value and future value. Present value, we just talked about it, is what a cash flow in the future would be worth to you today. And you can use it to answer questions like, you want to have $10,000 in 6 years. How much should you deposit today in your savings account, given a certain interest rate, in this example is 5%, so that at that point in time you will have $10,000. Future value is kind of the reverse. It's telling you if I have a certain amount now, so that is my present value now, and I can earn a certain interest rate on my account in a certain amount of time, like in 6 years, what will that amount, what did that account grow into? Like if I deposit $1,000 now, when I leave it there for 6 years at 5%, in the end, how much will I have in my account? This is, I have a certain known present value, and I want to compute what the future value of that amount will be at a certain point in time. So, goes without saying, if you are confused about these two things, if you confuse one for the other, everything else is going to become very, very confusing. And I mean, maybe you are not confused and you think it's pretty obvious, but I can tell you, when I was teaching the fall semester, even into November, I still had people like, what's future value? Asking me. So that makes it very hard to understand everything else. Okay, we already said what future value is. Also a note, in the chapter at some point, before talking about compounding interest, you are introduced to the concept of simple interest. You might get exercises with it, but almost everything else we do, basically everything else we do in this chapter, is using compounding interest. So what is a simple interest? A simple interest is an interest that you only earn on the original amount. And basically, you do not earn interest on interest. So it's clear, making an example, you have $100 and you receive 6% simple interest on your account. You deposit $100 and you receive 6% simple interest. That means that you receive every year, forever, $6. That's 6% of the $100 you deposited in the account. So as you see, year after year, your account grows by $6. You can keep your money there for 1,000 years, and every year it will grow only by $6. So there is no compounding. There is no interest earned on interest. The only interest producing amount is your original $100. Okay? Compound interest is instead a scenario in which the first year you earn 6% of your original $100, the amount you deposited, but from that point on, you earn 6% of whatever is in your account. So the second year, you earn this 36 cents relative to what you were earning with simple interest. You were only earning, again, 6 and 6 and 6 forever. Here, you start to earn this amount, which is the interest on those $6 that you earned the previous year. So as time goes on, you see the interest earned grows and grows more and more, because you're also earning interest on the interest you received the previous years. So this is the type of interest that we will be using whenever we do computations in this chapter, unless you're specifically told by your exercise you only earn simple interest. Okay? Okay. So compound interest is very powerful. Here you see the future value of $100 as time goes on with different interest rates. This is with 0 interest rate, you don't earn anything. You keep your $100 forever. There is no interest being paid. But you see, as interest rate grows from 5 to 15, these different lines, in the beginning, doesn't look like there's a big difference. I mean, sure, 15% always means more interest than 5%, but you know, as long as your horizon is 4, 6, 8 years, the difference, well, 6 years, the difference is not huge. But as you see, as you increase the amount of years that your account is generating interest, in the end, the difference is really great. This is because at some point, the interest on interest component is actually more significant than your original $100. So the first question that you had to prepare for today is you put $700 in a savings account with 10% nominal rate of interest, compounded monthly. What will be the investment? What will the investment be worth in 21 months? Round to the nearest dollar. So first of all, is this a present value or a future value question? Future value, right? I have some amount today that I precisely know, $700. I put it in some account that generates interest, and I want to know how much will I have at some future point in time. In this case, in 21 months. All right, seems pretty straightforward. The only complication is I'm given a 10% nominal rate of interest. That's a yearly rate, right? But the compounding is monthly, and I want to know the future value in 21 months. So what do I need to do? You divide the yearly rate by 12, and you get a monthly rate. Okay? And then, for example, on the calculator, what would you do? What would my present value be? Negative 700 on the calculator. So the interest rate would be 10 divided by 12. PMT would be 0, because I don't have any recurring payment here. What's left? How many periods do I have? What's my N? 21. And then I solve for future value. Perfect. And when you do this, you get 833. This is pretty easy. In my experience, a lot of mistakes happen because people forget to do this. They put 10% as the interest rate, and in that case, you know, the calculator doesn't know this is months or years or anything. It knows 21 periods at whatever interest rate you put. So if you forget to do this, you are actually applying a 10% monthly interest rate, and you get a much higher result. Okay. You can also not do it on the calculator and just apply the formula. You have some present value, you have an interest rate, and you have an amount of periods. So you plug 10 divided by 12 as your monthly interest rate, 21 periods, 700 is the present value, and you'll get the same. Okay? All right. So we saw this graph earlier that showed how a higher interest rate generates much higher future values as you extend your time horizons. And here we're seeing kind of the the other face of the medal, you see the effect of discounting at different interest rates as your time horizon becomes longer. Like, imagine you are receiving $100 at a more and more distant point in time in the future, and these lines tell you what your present value of those cash flows would be at different discount rates. And as you see, as the discount rate becomes higher, the present value of those cash flows drops. And the effect is larger and larger the more into the future you move. Because discounting by a very high interest rate an amount very distant in the future means you really drop the value a lot. And you can start, I don't know if it helps you, but it definitely helps some people. Just look at the formula. You see the interest rate is at the denominator is what is cutting down, reducing the future value. So the higher this value, the lower the present value will be. And it gets raised to the t power. So of course, as t becomes larger, the effect becomes even larger. Okay? So higher interest rate means the present value will drop more as the interest rate becomes higher. And since I'm raising it to the t power, as t increases, which means as we move the cash flow more and more into the future, this effect will be magnified. Okay? So if something is coming very soon, the effect of different interest rate is not that big, but the more you move into the future, the more you see this large spread. Okay? I lost a lot of time telling you this because I think it helps a lot if you kind of ingrain, like deep inside you, that high interest rate makes present value drop, and this effect will be larger and larger the more I move it into the future. It will be very useful to really be comfortable with this idea when we move into bonds of different maturities, for example. And we will see later the price of bonds react differently depending on the maturity they have when interest rates change, and being comfortable with this concept will really help you understanding that. Okay, 3 years from now, Barbara Waters will purchase a laptop computer that will cost $2,250. Assume that Barbara can earn 6.25% compounded monthly on her money. How much should she set aside today for the purchase? So this is a present value question, right? We have some future value, and we want to know how much should we set aside today so that given a certain interest rate that we can earn, our money will grow until it will become this at a certain point in time. We want to have $2,250 in 3 years. We want to know what amount should we deposit now so that earning this interest rate month after month, in 3 years, we will have exactly that. So how can I solve this? Yeah.
Do we multiply the rate by 12?
Multiply the rate by 12. Divide it, right? This is a yearly rate. We want a monthly rate. We divide it by 12, and we get Okay. And at that point, we have a choice. We can solve it using this formula for present value, because we know everything. Or we can use the calculator. If I were you at this point, I would do both when, solving exercises, because sometimes one is faster. When the exercises will become more and more complicated, the calculator is quicker. But I think doing at least some of the exercises only with the formulas kind of ingrains into your mind where the numbers come from, like what is the shape of the formula. So we have 36 months. That's 3 years. The interest rate for each month we find just by dividing the yearly rate by 12. And we have the future value. There are no payments. And we solve for present value. Okay? And we find 1,866. This means if I have $1,866 today, given that this is the interest rate I can receive on it, I put it there, and in 3 years, I will have exactly the $2,250 I need to purchase the laptop. Okay? You could have very different exercises that you would solve in exactly the same way. If I was telling you, I am going to pay you $2,250 in 3 years, what amount would be equivalent to you today? Like, you know, I could tell you, I either pay you $2,250 in 3 years or some amount today. What amount would be equivalent for you? What amount today would be equivalent to you to receiving $2,250 in 3 years? 1,866. Why? Because if I pay you now 1,866, you can put it in your bank account, and in 3 years you will have exactly 2,250. So the two scenarios are really equivalent. In one case, you do nothing, you wait, and in 3 years I pay you 2,250. In the other case, I give you the money now, and in 3 years, given this interest rate, it will grow exactly to the same amount. Okay? So present value questions, you know, can both ask you about the value of something you need to receive in the future, the value today of something that you will receive in the future, or ask you what amount should you set aside today so that you will be able to afford something in the future. At what rate must $400 be compounded annually for it to grow to $716.40 in 10 years? Okay, how do I solve this?
We have present value and future value. Present value is going to be a minus, and we have the years.
Yeah.
So it's saying annually, we have annual %, so we get 6%.
Yep. Did you hear him? No? So in this case, we both have present value and future value. So on your calculator, you can input both. We have 10 years. That's the time. We don't have to adjust the number of periods in any way because we are told the interest rate, the compounding is annual. And we just solve for the interest rate. Compute. Oh, no. Wake up. Just a second, because I have... Yeah. So we have 10 as the number of periods. 400 is our present value. 716.4 is the future value. 0 is the payment. And we solve for the interest rate. And we get 6%. right? So when things become more complicated, yeah.
You always have to remember to put in the present value as a negative.
Yeah. So, okay, what happens? What else could you do? The calculator doesn't care that you put it negative. If you put it positive, you need to put that one negative. It's just, if you read how the calculator computes things, it is trying to find the interest rate that makes these two cash flow basically turn one into the other. So the way I think about it, to be consistent, is the present value in this case is negative because I part from some money. I put it in an account. And at the end of the 10 years, I receive back 716. But you could reverse them, and the calculator will give you the correct answer. You need to be consistent in your reasoning once you have a third variable like payments, because at that point, if it has to agree, because in this case, if you put a payment negative, it's the same direction of cash flows as the present value. If you put it positive, it's the same direction of this. So in one case, you are receiving money from, for example, an annuity, as we will see. In the other case, you are paying into it. Yeah.
Can you show us how to do the question 2 on the calculator?
You mean again? Yes.
The second.
The second one. Okay. Wait a second. Sorry. Okay. Question 2 is this. Okay. So, all right. So, how many periods do we have? We have 3 years. And we are doing months, because we have a monthly compounding account. So we have 3 years, but we need to multiply it by 12 to get the number of months, which is 36. That will be our n. Then we need to adjust the interest rate. We are given a 6.25% interest, but that's the annual rate. We need to divide it by 12 to find the monthly rate. So that's our interest rate. 0 is the payment. And we have a future value of 2,250. And now we compute the present value. Okay. So once the cash flows become more complex, either they are more, here they are all the same. This is just an annuity. I find it's very useful to draw the timeline, especially when you start being confused because you are told at the end of the 6th year this happens, and at the beginning of the 4th, and you're like, oh, I don't. If you draw it, it's much easier to understand it. All right. So an annuity, ordinary annuity, looks like this. This is a 10-year, $3,000 ordinary annuity. The payment all happen at the end of the year. Okay? So if you have $20,000 in an account earning 8% annually, what constant amount could you withdraw each year and have nothing remaining at the end of 5 years? So, all right. We are basically asking what in terms of present values and future values? What's the payment of what?
What's the payment of having
Of the
future value
What's the future value?
20 times 1 plus.
Nope. It's 0. Why is it 0? Because we are told we will have nothing at the end of the 5 years. What's the 20,000? That's the present value. This is basically asking, I want to know what payment I can withdraw, given that my present value is 20,000, my future value will be 0, and I have a certain interest rate. Okay? So you just input everything in your calculator and solve for payment. So you see, when you correctly identify, you go from the words of the exercises into the variables of the calculator, then, you know, it just takes 30 seconds to plug in everything. The real issue is understanding how the words translate into that, understanding which one is the future value, which one is the present value. Why is present? So the fact that future value is 0, for example, I know for a fact that a lot of people struggle with. They say, they constantly ask me, where does the 0 come from? The 0 just means at the end of the period, this structure will have nothing in it. I completely deplete my present value of $20,000 through the payments. I withdraw from this $20,000 up to the point that after 5 years, I have nothing in it. Okay? Yep.
So in this case, both PV and FV are positive?
FV is 0. When you solve for it, let's see, what do you think? Do you think a PMT will be positive or negative? It will be negative, right? But in fact, you could and maybe should, the $20,000 following my the way I remember things should actually be negative. Because I would think I put down $20,000 in an account and I will receive positive some payment. The calculator doesn't care at all, though. It's just a way I try to be consistent, not to get confused. 0 is the future value, compute, and you get it positive because, you know, we are withdrawing. But of course, you can also put present value positive, and you will get the payment negative. Okay? So effective annual rate and annual percentage rate. We actually kind of already did this in the previous exercises. The annual percentage rate is also called the stated rate. It's telling you a yearly rate without considering the compounding. The EAR is effective, meaning that if you put $1 in the account and you wait for a year, the EAR is what you will have in your account. It's the effective rate that you see your account is growing by, because it does consider the compounding. APR will be the same no matter what the compounding is. I mean, I will tell you it's 10% compounded monthly, compounded quarterly, compounded daily, but it remains 10%. If you want to see what the effective rate corresponding to that is, you have to compute it. You have to consider how many times per year it compounds, apply the formula, and find it. So from the formula, you should see that the higher the frequency of compounding, the higher the EAR will be for the same APR. Like if, let's fix this at 10%. If I compound yearly, I will have a 10% EAR also. If I compound semi-annually, my effective rate will go above 10% a little bit. If I compound monthly, it will be even higher. If I compound daily, even higher, up to the point where I have something called continuously compounding, which we will see in a couple of slides. That is like the highest effective rate you can have given a certain APR. But we'll see it. Okay. But this question says the EAR is known to be 16.08% on a debt that has quarterly payments. What is the APR? How do I do this? Yeah.
I know how to do a calculator.
Okay, how do you do it on the calculator?
You hit second, and number 2, it says ICONV. And then you have effective. Well, effective is going to be 16.08.
Yes.
Press enter, and then for rate is going to be 4 because it says quarterly, so it's 1 year is 4.
Perfect.
And
So
then you compute the NOM.
that's right. Perfect. Which is this. So your calculator has a function to do this. You're basically telling the calculator to do second function icon V. You're basically telling the calculator my effective rate is 16.08 and the number of compounding periods per year is 4. Give me the nominal rate. Okay? That totally works and might or might not be quicker than applying the formula. Okay?
How do you do it? Can you show us on the calculator?
Second function icon V. And then you have to use the arrows above to input effective rate 16.08 and number of periods per year equal to 4. You need to do enter. After. Nominal.
Can you show us on the calculator?
Can you demonstrate?
Yeah. Okay. Yeah. Okay. So here we have effective, which is 16.08, I think. Yeah. Enter. The number of compounding periods per year is 4. Enter. And you compute the nominal. Okay? Now, I still think that is worth doing it this way at least a few times because or you practice a lot on the calculator. Because, again, at least my students, they would mess up a lot with the calculator when they were like under stress in the exam and trying to go fast. The calculator is really amazing, but if you want to use these functions, be sure you practice them before the exam. Don't just think, oh, I know the calculator somehow can do it, but I don't actually remember if I have to press enter or compute before or after, because then it becomes a liability actually. So whatever function you want to use on the calculator, be sure you actually practice it. What is the annual compounded interest rate of an investment with a stated interest rate? When you read stated interest rate, you know that's the APR of 6% compounded quarterly for 70 years. All right. So what do I have here? I have the APR, and I have the number of compounding periods per year, which is 4. So I can do the same thing I did before, but now I have the nominal and I want to solve for the effective rate. Or I can just apply the formula. In this case, it's even more straightforward than before because I have everything on this side and I just solve for the EAR. Okay? Yearly rate, stated rate divided by 4 because I'm compounding quarterly, so I have 4 periods per year. 1 plus that, I raise it to the 4th power. That is 1 plus my EAR. Whereas here, if you do the math, it's a little bit more complex because you have to free this variable from the 4th power. You have to take the 4th root of both sides and then do the algebra. The 7 year has nothing to do with it. Yep. Say it again.
I was going to say, can you pull up the formula again? Why does the 7 years do with it?
Where would you use it?
Determining the amount of periods.
Say it again.
Determining the amount of periods. It's quarterly, so 4 times a year for 7 years.
So that would matter if I were asking you, if you put $1 in this investment account, what does it grow into after 7 years? But here we are just trying to figure out what is the effective rate of return of this investment account, given that the only thing we are told is a stated rate for the year, but actually this account compounds quarterly. So each one of the 7 years, we will earn this effective rate. So the fact that it's a 7-year investment would matter if I actually asked you, by putting $1 in this investment account, how much will I have in 7 years? Then yes, then you would use 7 as your number of periods. But here, I'm not asked anything about that. I'm just saying, I'm just asking, what is the effective rate of? Why? I think to confuse you a little bit. Yeah.
What did you get for this?
What did I get for this? 6.1. Let's see it. .06 divided by 4 plus 1 to the power of 4. Yeah, because sorry, I need to increase the number of decimals. So 0.06 divided by 4 plus 1 to the power of 4 minus 1. This is on the calculator doing it following the formula. I didn't use the function that the calculator has to compute the EAR. I just followed this formula plugging in the numbers. I did 0.06 divided by 4 plus 1. What I get to the power of 4 minus 1 gives me the EAR. Okay? You are considering two investments. Investment A yields 10% compounded quarterly. Investment B yields R% compounded semi-annually. Both investments have equal annual yields. Find R. What is this question asking? The interest is very vague. What interest? It is telling you the EAR. When it says both investments have equal annual yields, what rate is that referring to? You think the APR. But here it says R% compounded semi-annually, while investment A yields 10% compounded quarterly. So this 10%, is it an APR or an EAR? This is EAR, you think? Let's go back. Let's go back to the wording here. There's an investment with a stated interest rate of 6% compounded quarterly. It's telling you some rate, and then it tells you the compounding. And using these two pieces of information, you can find an EAR, an effective rate. If this 10%, this 10% was effective, it would already be an EAR, and you wouldn't need to know it's compounded quarterly. It's relevant that it's compounded quarterly because those two pieces of information together allow you to compute the effective rate. So this 10% is an APR. So for investment 1, I have 10% compounded quarterly, and that translates to an effective rate of 10.38%. Okay? Now we are told that both investments have equal annual yields. This is telling us both investments have the same EAR. So I can use this piece of information that I just computed for investment 1 as the EAR of investment 2. Sorry, investment B. And what I do not know is R%, the APR of investment B. So the steps are, I know that investment A has a certain APR, 10% in this case, and I know the compounding period, quarterly, so 4 compounding periods per year. And I know that investment B has the same EAR as investment A. Yeah?
Will these slides be posted online?
Yeah. Yes.
Where?
When?
Where?
Where? This is a very good question because I can post them in so I can send them to your professor saying these are the slides, can you post them? At that point it depends on them whether they want to or not, or I can post them in the Excel page of, so your, that I can access directly. I can also do both. Which is always the best thing, both. So, what does it mean that these two investments account have the same EAR from like an investment perspective?
Both compound the same amount of interest yearly, annually?
It means so investing in these two vehicles would give you the same return. Like at the end of the year, you would see the same amount of money. They net you, they give you, your return is 10.38% for both of them. So as investments, they give you the same return. The difference is one of them is a 10% interest rate compounded quarterly. The other one is a 10.125% compounded semi-annually. See, this interest rate is higher, but the compounding period is lower, is less often, only twice per year. This one has a 10% interest rate, but is compounded 4 times per year. And in the end, these two turn out to have the same effective rate. I mean, we were told that they had to have the same effective rate. So this is basically telling you 10% compounded quarterly is the same as 10.125% compounded semi-annually in terms of what you actually see at the end of the year in your bank account if you had deposited as $100 in both of them. You would see the same return. You would see $10.38 for each $100 you deposited in each account.
So the answer is C, right?
The answer is C. Yeah.
Is there a way to do this in the calculator the same way we did the other ones?
Absolutely. You do so for the first one you want to compute the EAR. So you do second icon V. No, sorry, second icon V. So the nominal is 10%. And you have compounding period 4. Sorry, I didn't clear. So the nominal is 10%. Enter. Compounding period is 4. Enter. Compute. No, sorry. You want to compute the effective. And you get 10.38.
But how you got the answer 10.1?
So let's do it again. I clear everything. Here it is asking me the nominal rate. The nominal rate I know is 10%, right? I input 10, enter, and then I scroll down. This is the compounding periods per year, which is 4. Okay? The third variable is effective, which is what I'm looking for, so I do compute. And when I click compute, it solves for the, you basically have to give the calculator 2 variables and solve for the third. Okay? So now that I have effective rate as this, I can go and change the compounding period to 2 and then solve for the nominal, and it will give me the same answer that we had here using the formula. Yep.
My calculator only does 2 decimals. Is there going to be an issue for that?
You need to do second format, which is where the dot is at the bottom. And then I'll show you. Yeah. At least one of your professors specifically asked me to check all the answers using 4 decimal spaces. So I would assume that that's how she computes the answers for your exams also. So put it to 4 decimals. You don't care? I was like, okay. Yeah. You want to travel to Europe to visit relatives when you graduate from college, 3 years from now. Okay, so in 3 years you have to spend some amount. You want to be able to spend $10,000. Okay, your parents have deposited $5,000 for you in a certificate of deposit, paying 6% annually. So, okay, you will have 2 sources that together need to amount to $10,000 in 3 years. one of these two sources is $5,000 invested at 6% for these 3 years. Okay? Then you also have an aunt who is giving you some unknown amount that will be invested at 10% for 3 years. You want to know what this unknown amount needs to be. Basically, you're asked, how much do you need to invest at 10% for 3 years such that together with also this $5,000 invested at 6%, those two investments together will add up to $10,000 in 3 years. Okay? You have one portion of this setup which is fixed. You know everything. You know the amount, $5,000. You know the interest rate. So you can compute the future value of this portion. You know that altogether you want to have $10,000 in the end. So you can subtract from $10,000 what this $5,000 will grow into in 3 years. And whatever you find, you need then to discount back to find what you need to invest now. So this starts being a little bit more complex an exercise. So you have some future value, $10,000, that will come from two different sources. One of which is $5,000 invested at 6% for 3 years. This portion has everything known. You can compute the future value of this $5,000. I have $5,000. I invested at 6%. How much will I have in 3 years? Cool. We can do it. We do 5,000 is my present value. Go away. 0 is the payment. 6% is the interest rate. 3 years is my period. Compute future value. I got some number. Okay? Which is this number. So this is how much will I have in 3 years from this $5,000 that my parents invested for me in certificates of deposits, which earn 6%. But this is not enough. I want to have $10,000. So 10,000 minus this amount that I just found is the portion that I still need to figure out a way to get. And I was told my aunt can also give me money that will be invested at 10%. How much money do I need to invest at 10% now so that in 3 years they will cover this amount? So how do I do it? I have $10,000 minus 5,955.08. This is the amount that I still need somehow to finance, to figure out a way to get in 3 years. So this is my future value. 3 is the number of years. 10% is the return on this investment. 0 is the payment. Compute present value. This is the amount that my aunt needs to put down at 10% now so that in 3 years it will grow to this amount. The part of the $10,000 that is not covered by my parents' gift of $5,000. Yeah. this is a good exercise, meaning this is the kind of exercise that you could see in a final or in a midterm, and yeah.
Negative.
Why is the PV negative? Because I put the future value positive. Kind of makes sense, like you put in the bank 5,000 and it will grow into, it will come back. So receiving the payment and putting money in the bank, if you think about it, have two different directions, have two different signs. So what is important about this exercise is that you understand the reasoning at this level. You have some final result that you are told. You need to have $10,000. You have two sources that added together need to give you $10,000. One of the two sources has already a present value that you're told. Your parents give you $5,000. You can put it down at 6%. There are no variables here. There are no unknowns. It's $5,000 present value. 6% is the interest rate. 3 years, you can compute future value. Everything is known about this portion. Then you will see this is less than $10,000. So some other amount must come from a different investment. The investment is at 10%, also for 3 years. But you're asked, how much does this need to be? The present value of this. How much does your aunt need to put down now so that in 3 years it will cover the difference between $10,000 that you need to have and whatever your parents are covering? It's like the two sources together need to add up to 10,000. So it's not hard, but it can be confusing how to use all the information that you're given in the text in a way that kind of makes sense. And to me, drawing the timeline is the best way to see it. Even though you don't have payments here, so you look at it and it looks kind of useless but you can draw a squiggle line and say, okay, write it down. This is what this part of the investment gives me. Now I want to find this other part at 10%, and it together with this is to give me $10,000. California investors recently advertised the following claim. Invest your money with us at 21% compounded annually, and we guarantee to double your money sooner than you imagine. Ignoring taxes, how long would it take to double your money at a nominal rate of 21% compounded annually? Round off to the nearest year. How do you do this? Yeah.
I put 1 as my present value.
Yeah.
2 as my future value.
Yeah.
21 as my I. Payment at 0. My computer N.
Perfect. So he said I put -1 as my present value and 2 as my future value, 0 as my payment, 1 as my number of years. No, sorry, 21 is my interest, and I want to compute the number of years. I don't think really that 3.6 years is approximately 4. I think they're quite different, but it was the closest answer. So if it asks you to round to the nearest year, and you're asked by an exercise, how soon can you afford to do this, or how soon will you double? You want to round up. I know here it says round to the nearest year, but even if you got 3.1 or 3.2 years, and the exercise asks you in how many years you will have doubled, you need to wait for 4, because at 3 years you haven't doubled yet. You need an extra half year and more to actually double it. So with the rounding, sometimes there's at least one exercise in your book that has a setup like this, and you actually get to something like 5.1, but the answer is 6, because at 5 years you still haven't reached the objective. Something like how many years before you can retire. If you need a certain amount, at 5 years you haven't met it yet. You need to wait the 6th year. There's also the rule of 72. I don't know if you remember it. The rule of 72 means that you divide 72 by the interest percentage. So in this case, it would be 21. And that's roughly the amount of time to double. So in this case, you would just have 72 divided by 21. You get 3 point something. More than 3 and less than 4, basically. It's not super precise. It's just a back of the envelope kind of computation that I think it's useful mostly to understand if you're wildly wrong about your result. If you made some mistake and you're like, oh no, wait, with this interest rate, if you have an 8% interest rate, the rule of 72 kind of gives you a ballpark idea of how quickly you should double your money. So if you are doing an exercise and you realize your money is growing too fast for the percentage rate you have, then maybe this will catch your mistake, help you catch your mistake. Okay, annuities due are simply annuities where the payments happen at the beginning of the period as opposed to the end. To compute present value or future value, you can use the begin function of your calculator, of course, or you can also multiply by 1 plus r the present or future value of an ordinary annuity. Basically, the values for present value and future value of annuities due are just off by a factor of 1 plus r. Okay? The reason why is pretty obvious if you draw the timelines. An annuity due is really an ordinary annuity where you take the payments and you bring them forward by 1 period. So each payment stays there and earns interest 1 extra period. So this 1, 2, 3, 4, 5, 6, 7, 8, 9. If you count for the annuity due, the first payment earns interest 10 periods, not 9, and so on for each one of them. So each payment earns interest 1 extra factor of 1 plus r. So in the end, that's where this comes from. Okay? Yep. Depending on how you feel, this could actually be easier than setting your calculator to begin if you are the type of person who then forgets to put it back to end and goes on to make a mistake in every following exercise because the calculator is still set to begin when it shouldn't.
If you reset, it goes back
If you reset, it goes back to end. I mean, you need to do this. You need to, so now you set it to begin. If you clear, it doesn't go back to end. You actually need to do set it to end, and now it's back to end. The only thing that tells you you are in begin mode is this BGN there. Like, in my opinion, it should be pink and flashing, because I know it's so easy to, you know, forget it's there. And so I don't know. I remember some students told me I do everything in end, and then if it's an annuity due, I multiply by 1 plus r. That's the factor they're off by, but I compute everything in. I'm not telling you you should. I'm just telling you, if you are the type of person who makes this type of mistake, forgets in, you know, in which forgets to bring the calculator out of begin mode, like systematically does this type of mistake, then maybe it's worth knowing this is the factor they're off by. And what is the present value of an annuity of $27 received at the beginning of each year? So this is an annuity due the moment you see at the beginning of each year. That's what it is for the next 6 years. The first payment will be received today, and the discount rate is 10%. Round to the nearest $10. So how do I do this? You set the calculator to begin to compute the annuity due. Okay? 6 years, 10%, payment is $27, future value is 0, and you solve for the present value. Let's do it. Second, begin. Okay, so I have 6 is the number of periods, 10% is my interest rate. Go away. 27 is my payment, and solve for present value. So it's option A. Perpetuities. You have only seen level perpetuities until now, they told me, or maybe now you've also seen growing perpetuities in chapter 7. But anyway, they told me in chapter 5 you only see level perpetuities, and only to cover those. Perpetuity is really just a stream of level cash payments that never end. Yeah. Can I go back? Sure. This is empty. And this one? What's unclear? Yeah. No. Is it okay? Yeah. Okay. So the present value is wonderful because you just take the cash payment, divide by the interest rate, and you're done. What's the future value of a perpetuity?
Like 0 infinity?
It's that we don't compute it, right? Because it never ends. If I tell you what's the future value after 3 years of this stream of level payments is not a perpetuity anymore because I'm putting an end to it. I'm computing basically a piece of it, which is an annuity at that point. A perpetuity, by definition, never ends. Yeah?
What's a real-world example of a perpetuity?
I'm glad you asked this because for a while I got very excited because there were actually some British perpetuities that were real-world things. They were issued, I think, in the late 19th century, and they were forever. You would own this piece of paper, said the British Crown will pay you a certain amount forever. And unfortunately, I think in 2014 they actually purchased them back, and they are not circulating anymore. However, the real-world use of this you will see in when you try to value stocks. Think about dividends that a firm will keep paying in the future. Like you're trying to value a stock of a firm that, pays dividends. Maybe you will actually want to model growing dividends, and that's why you will model using a growing perpetuity. But a level perpetuity will be a piece of the valuation you make of the stock, thinking, well, let's assume this stock will pay me this current dividend forever in the future without raising it, just this baseline level that I observe now. Let's see what it would be worth to me if they kept it going at this level forever. That's one example of using a perpetuity to model something that actually exists. You're going to pay, whoa, it's late. You're going to pay $800 into an account at the beginning of each of 20 years. The amount will then be left to compound for an additional 20 years. So for 20 years, you pay into this account at the beginning of each year. And then you leave everything as is for an additional 20 years, during which whatever you have accumulated there still keeps earning some interest. You just don't add to it. At the end of the 41st year, you will begin receiving a perpetuity from the account. Okay? If the account pays 14%, how much will you receive each year from the perpetuity? So who can walk me through the steps of solving this?
Sorry, it pays 14% of the total amount after or during?
No,
is
no,
that the
14%
APR
is the interest rate.
and that's calculated from day one, right?
Yep.
Yeah, so you do
So-
payment is 800.
Say it again.
Payment is 800.
Okay.
And it's 20.
So, okay, first thing, what are you doing now? You are computing what?
After 20 years. Yeah.
Okay. So, you said 800 is the payment?
Yeah.
Maybe negative?
You have it in BGN.
We are in begin.
Yeah.
We are supposed to, right?
Present value is 0.
I do whatever you say. Present value
I don't know.
is 0.
I don't know.
No, this is how it
Testing the
works.
water here. Interest rate is per year would be, what is it, 14?
I believe it's 14%, yes?
And it's 20, and you calculate future value.
Cool. Then what?
That's, now you take, that's your present value after 20 years.
That's my future value. That's what it says.
I'm calculating the second part of the,
Okay, then I take this amount.
this now would be your present value for the second part of the problem. Payment is 0. Interest rate is still 14.
Yeah,
And it's still 20.
yeah.
And then you calculate again the future value.
Okay. And then what do we do with this perpetuity thing?
It pays you 14%.
Nope. we want to know, so what is this big number that we just found? That is the future value, but in real world terms, what is it? It's the money you would accumulate if you actually did this. For
40 years.
For 40 years, actually for the first 20 years you pay $800, and then you stop paying into this account, but you still leave it there, and in the end, what would you find there? This amount. And now the value of the perpetuity is given by these two variables: the cash payment you receive from it and the interest rate. We are asking how much will this perpetuity pay us. We have the present value of it. We just computed it as the future value of everything that has accumulated there. And we do know the interest rate. Say it again? That's right. You take it and, yeah. So this is what we just did. Okay? I still have the number here, so I can show you it's actually the same thing. We did it right. Okay? And now we just multiply it by the interest rate to find the perpetuity payment.
Why is n not 21 for the second part?
Why is the n 21 for the second part? It isn't.
Not 21, because isn't it 41 years old?
Ha! See, I could tell you, but I won't. No, I can tell you. But what you should do is draw the timeline. Because actually, this is one of those cases when, I'll draw it here. When you have a perpetuity, when is the first payment happening? Nope. You have it here, right? So we compute, so at the end of the 41st year, if this is the 40th, this is the 41st. So the present value of this perpetuity is here at time 40. The perpetuity that starts at time 40 makes the first payment at time 41, which is the end of the 41st year. Just like, whoa, this is, I don't know how to delete. So let me try to explain it again. When you draw the timeline for any perpetuity, the first payment happens at time 1. That's the end of the first year. Okay? Now add 40 years to this. The first payment of a perpetuity that starts at time 40 is at time 41. Okay? So at time 40, you have this amount. That's our time 0. So if you have this amount at time 40, and you turn it into a perpetuity, the first payment actually happens at time 41, which is exactly what we are told should happen. Now, this can be extremely confusing if you don't draw it. This is the kind of situation in which it's very beneficial to actually draw what happens there and when does the payment start. Even for annuities. If it's an ordinary annuity, whatever first year payment you have, you know the ordinary annuity starts the period before, and if you have computed the present value, that's where you have the present value. No, even for present values. Let me erasable. I hope they are. I am trying and okay, yeah. So use the other one. This one doesn't really write. So 55, 56, 57, these are year, okay? Years. So let's say that you have payments here. You have $30 payments at year 55, 56, 57, and 58. If I compute the present value of these cash flows, I compute it as an ordinary annuity in my calculator. Where is the present value located in time? I'm computing the present value of these cash flows at time what? 54 here, because usually when you draw an ordinary annuity, you have year 0, and the first payment happens at year 1 and then 2, like here, right? So the ordinary annuity starts when you compute present value, you find it at time 0, and the first payment is at time 1. So here, the first payment is at time 55, and when you compute present value, you have it at time 54. So this lets you see, okay, if now I want to discount it back to time 0, how many years I have to discount it back? 54. Now, it's very easy to see because you drew it. Because if you were just told the first payment happens at time 55, maybe you would think, oh, okay, I have to discount it back 55 years. You can get confused very, very easily. It's much easier if you actually draw it and you realize, okay, whenever I have, see, whenever I have an ordinary annuity, the first payment happens at time 1, and if I were to compute the present value of this stream of payments, I would find the present value at time 0. So 1 year before the first payment happens. So in that case, the first payment, the first perpetuity payment is at time 41. So the present value that I need to equate that perpetuity to is at time 40. So 20 years plus 20 years. That's why here I don't have 21. Charlie Stone wants to retire in 30 years, and he wants to have an annuity of $1,000 a year for 20 years after retirement. So, okay. Charlie wants to receive the first annuity payment at the end of the 30th year. Using an interest rate of 10%, how much must Charlie invest today in order to have his retirement annuity? Okay. What's the first step? I want to fund something, right? There's something I want to receive in some future. I need to figure out how much that is going to cost me in terms, like how much money do I need to have when I want to start receiving those payments in order to be able to fund these withdrawals that I want to be able to make. I want to be able to receive for 20 years $1,000 a year. So the first step is, what do I need to have in order to generate $1,000 per year for 20 years? So my N is 20. Interest rate is 10, payment is 1,000, future value is 0. Solve for present value. This tells me, in order to be able to generate these $1,000 payments for 20 years, I need to have $8,514. When do I need to have that? Say it again. At the beginning of year 30. That's right. So I have 29 more years before that to earn interest. Right? So this present value now becomes my future value. And I want to figure out how much do I need now to put in the account so that in 29 years will grow into $8,514, which is the amount that I will need to generate for 20 years $1,000 per year payments to me.
This isn't beginning year break.
No. Because here we are not having any payment at all. This is just 29 years of interest being accumulated on whatever amount we put down now. Harry just bought a new 4-wheel drive Jeep Cherokee for his lumber business. The price of the vehicle is $35,000, of which he made a $5,000 down payment and took out an amortized loan for the rest. His local bank made the loan at 12% interest for 5 years. He is to pay back the principal and interest in 5 equal annual installments beginning 1 year from now. Determine the amount of Harry's annual payment. So $35, of which $5,000 we already paid today. Okay? What's left? $30,000. $30,000 we will pay back in 5 equal annual installments, the first of which in 1 year. That sounds to me like what? What type of annuity? 1 year from now, the first payment? An ordinary annuity, okay? That's really straightforward. Present value is $30,000 because it's what's left to pay back after the $5,000 down payment. 5 years, 12% interest rate. Future value is 0. Future value is 0 because after the 5 years I need to have paid back completely the amount. I want to know the payment. So solve for PMT, and I get 8,322, which is 8. Yep. I'm trying to accelerate because I'm late, but I can stay longer if there isn't another class coming in, which I don't know. Yeah. You are considering the purchase of a home that would require a mortgage of $250,000. How much more in total will you pay if you select a 30-year mortgage at 5.65% rather than a 15-year mortgage at 4.9%? Okay. So how do I compute? So there are 2 different possible mortgages, right? One of them is a 30-year one, and one is a 15-year one. The 15-year mortgage actually also has a lower interest rate. So I want to know how much more will I pay.
And then you minus them?
The payment, right? Calculate the payment.
You need to calculate the payments and then add them all up. and subtract them one from the other. So the present value of these two mortgages is the same. The present value is $250,000 in both cases, right? The future value is also the same, because what's the future value for them?
0.
Is 0. So what is going to be different is the payments. So I can solve for the payment in the two cases. Now, there are many occasions to make a mistake if you don't pay attention here, because remember, these are monthly payments. So N is 360 in one case and 108 in the other. That's 30 years times 12 and 15 years times 12. And I need to adjust the interest rates accordingly. Divide the yearly rate by 12 to get monthly rates. But once I've done that, there's really nothing else. I just solve for the two payments. And then I'm asked how much more am I going to pay in dollars, like effective dollars that I throw out at this mortgage over the course of it. I just multiply the monthly payment by the amount of months, by the amount of years, and 12 months per year to get the total. So in one case, I actually hand to whoever financed this mortgage $519,000 over 30 years. In this case, $353,000 over 15 years. So the difference between the two is $165,994. Now here, the exercise specifically asks you for this. What's weird about this? Okay, but what's weird about this? What am I doing here? Here I'm comparing. So this number is much lower, but it's also concentrated in 15 years. Meaning all these dollars that I gave to somebody are within 15 years. Here, part of these dollars are paid in a very distant future. And we know from time value of money that the value of dollars in the future is less than dollars closer to us in time. So I'm saying this because this is not telling you this mortgage is better for everybody no matter what, because you hand over less dollars. Because all these dollars you hand over in 15 years, within 15 years. Here, some of these dollars you're paying 25 years after the beginning of the mortgage. Continuous compounding, you need to know how to compute it. It's just e to the power of the quoted rate minus 1. So a sum of $5,000 is deposited into an account paying 8% interest continuously compounded. If $500 is withdrawn at the end of year 1 and 2, how much then remains in the account? How do I do this? There are many ways to do it, but
Two payments, 500.
what do you put for periods? No, I'm sorry, what do you put for interest rate?
Calculator, right?
You have to calculate it, right? So the first step is I need to know what the effective rate is, given that I have an 8% stated rate continuously compounded. And if you do e to the power of 0.08, you get 0.0833. Okay?
Where is E on the calculator?
you have the function e to the x. Yeah.
One slide when you get a chance.
I'll post them. So you can do this in many different ways. You can compute the future value of $5,000 after 3 years given this rate, and then subtract the $500 compounded for 1 period at this rate, and the $500 at the end, which is what I've done here. This is the future value of $5,000 earning this rate for 2 years. Minus 500, this is the $500 I take out at the end of the second year. And 541.6435 is the future value of the $500 that you take out after the first year.
Why isn't the second year compounded?
Because the second year is, I'm at year 0, right? $5,000. Yeah. Earn 1 year of interest, and then I take out $500. Okay. Another year of interest, I compute everything and take out $500. The second $500 is taken out right before I look at what's left.
How do you know there was 3 years? Determine future value.
There is no third year. At the end of year 1 and 2, and how much then remains in the account.
So you're doing finding future value of the 5,000. You do 2, n is 2.
Yeah. Now another way to do it, which is what I would probably do if I had to do it, is start with $5,000 and multiply by 1 plus r. Then subtract 500, and then multiply what's left by 1 plus r, then subtract 500. Like on the calculator, it will look like this. You have just for a matter of principle. So you have $5,000, right? And you multiply it by, what's the interest rate? By this amount. This is what you have after 1 year of interest given an 8% continuously compounded rate. This is the factor, 1.0833. So at the end of the first year, you have this much. And then you subtract $500. This is what you have after withdrawing the first $500. And now again, you multiply it by this factor, because this is how much interest you get from 1 year of continuously compounded 8% interest. This is what you have at the end of the second year before you withdraw for the second time $500, which now I do. And you get the same number.
So in the problem, you withdrew 541 and then 500.
Nope. I withdrew twice. I withdrew twice for 500. The reason why this is 541 because it's the future value of that. What I can you see here? What I did is this. I have $5,000 that and I compute the future value of those. Here I have negative $500 and I compute the future value of those. and here I have $500 negative. So what I do is subtract from my future value of $5,000 the future value of this negative cash flow that I have at time 1 and $500 negative cash flow that I have at time 2.
Can we use that formula with just payments equal to 500?
Say it again?
The formula that you gave us, and can we just put the payments at 500, future value at whatever?
Sure, you can do that.
Still give us the same thing, yeah?
Sure. Yeah.
We subtracted 5,325 in the calculator when you were gone.
When I was gone, where?
When you multiply 4,916 times 0.833, and then just subtract.
Yeah. So the way I showed it, maybe confusingly in the calculator earlier, is you can also do this. The factor, so if you want to know what $5,000 grow after 1 year into, given that interest rate, you do e to the power of 0.08, and you get 1 plus 0.0833. Okay? Each year that the $5,000 stay in this account, whatever is in this account grows by this much. This is the factor of growth. So what I did earlier is I have $5,000 at time 0. After 1 year in the account, I have this much. Whatever I find is my future value at time 1. Then I subtract $500. I do it on the calculator and I keep going. Whatever I find, then I multiply again by 1.0833, and then again I subtract $500. So the way I like it is because I see sequentially what's happening. I say, okay, I have $5,000. After 1 year, it will grow by a factor of 1.0833. Enter. I see how much it is. Now I subtract 500. Then I earn interest another year. Then I subtract 500. And sequentially, I see it. It is literally how you do these kind of things when you are in elementary school and you're like, okay, I subtract 1, and then I add 5, and then I subtract 3. And I keep track of the time, what happens at each moment. But it's the same thing as computing the future value of each cash flow. You bring everything at time 2. This is the future value of the $5,000 at time 2. This is the future value of the first 500 withdrawal at time 2. And this is the future value at time 2 of the second $500 withdrawal, which happens at time 2, and that's why it doesn't change.
The first one, that's yeah. 5,000 times 1 plus the rate to the second power, right?
Yeah. If you are computing it by itself, you just do this. This is the future value of the $5,000 is just 5,000 times 1.0833 to the power of 2. Sure. When comparing annuity due to ordinary annuities, annuity due annuities will have a higher what? Future values. Annuity payments, present values, both A and C, all of the above. Who said all of the above? I heard you. Will an ordinary annuity, will an annuity due have higher future value relative to an ordinary annuity? By how much? By a factor of 1 plus R. What about present value? You multiply by 1 plus R. Remember I told you both the future value and the present value differ by a factor of 1 plus R. So it will have higher future value as present value. What about annuity payments?
Less, could be less years payment, because the future value of each payment is less over time. Because first payment.
There is nothing that tells you how that would be different or equal. So if it's the same annuity, the only difference is one is an ordinary annuity and the other one is the annuity due. It is exactly the example we had here. The payments are the same. This was a $3,000 per year, 10-year ordinary annuity. This is a $3,000 per year, 10-year annuity due. Still $3,000. That doesn't change by making it an annuity due. The only thing that changes is when are the cash flows happening, beginning or end of the period. So, A and C. Yep. I will post them. Okay. The present value of an annuity stream of $100 per year is $614 when valued at 10%. By approximately how much would the value change if these were annuities due? 61.40, that is correct. How did you come up with that number? Again, the difference is a factor of 1 plus r. In this case, 1 plus r is 1.1. So 1.1 times 614 is 61.4. Okay? An investment offers to pay $100 a year forever, starting at the end of year 6. If the interest rate is 8%, then what is the investment's value today? How do I do this? Very good. So the first step is, this is a perpetuity, right? There is some investment that will pay $100 forever. So the first step is I want to attach a value to this investment. $100 divided by 8%, 0.08. And I can compute the present value of this perpetuity, which is 1,250. Now, when is this present value at? So the first payment is made in time t equals 6. So the present value of this perpetuity is at time t equals 5. Again, do you see why? If we were valuing a perpetuity that starts at time 0, the first payment would happen at time 1 year from now, and the present value would be at time 0. Here, the first payment happens at time 6, so the present value is at time 5. The first payment of the perpetuity is 1 year after the point where we value the present value.
Why don't you do beginning mode?
Beginning mode for what? The way I value the perpetuity is I'm not using an annuity due to do it. I'm just, payment divided by interest rate. So after I have this amount, I need to discount it back 5 periods. So to do that, what is this? On the calculator, I have 5 periods. 8% is the interest rate. 1,250 is the future value. 0 is the payment. And I compute the present value. Now, you can also just do 1,000. I don't know what it's doing. You can also do 1,000. I think it crashed. You can also just discount 1,250 by 5 periods. I, on purpose, did it like 5 times to show you each year, bringing it in back in value each year, step by step. I mean, you would do 1 plus r to the power of 5 and divide it by that factor. So, how much more is the perpetuity of $1,000 worth than an annuity of the same amount for 20 years? So this is saying there are 2 securities in a sense. One is paying $1,000 forever. The other one is paying you $1,000 for 20 years. How much do they differ in value? It's basically implicitly telling you what is the value of those extra payments happening more than 20 years from now. Because they both make the same payments for 20 years. One of them keeps going, the other one doesn't. So, the difference will be the value of the extra payments. So, how much is the perpetuity worth? 1,000 divided by 0.1, yeah, 0.10, which means $10,000. The annuity instead, I can compute. I have 10% the interest rate, 20 years period, and $1,000 is the payment, and compute. Ah, you're not seeing it because it's here, sorry. 10% is the interest rate, 20 years, $1,000 is compute present value, and you get that. So the difference is $1,486. It's not that much relative to the value of the perpetuity itself. Like the first 20 years, as you see, are 85% of the value of the whole stream of payments. Does it make sense to you? I mean, one of them pays forever, but it seems the added value of those payments is not that much. Why is that?
Growth rate?
Say it again.
There's no growth rate.
There is no growth rate, but still, they will. Yeah, okay. So what?
Therefore, the money's only growing at a set amount every year. I mean,
It's not growing at all.
Growing at all.
You're only
And
getting
the
$1,000.
The further you go in time, the less money the $1,000 becomes. So
Yeah, you are discounting more and more as this
So as
payment.
21 years
Yeah.
in, 30 years in, it's becoming the $1,000 becoming less relevant as the further you go.
Yeah. Yeah, think about it. Think about how little would you value if I told you, and I'll add to this annuity an extra payment in 300 years. Just one that happens then in 300 years. You discounted 300 by a factor of 1 plus r to the 300, it becomes something really tiny. Or if you don't want to think it in these terms, just think, how much do you actually care about something happening in 300 years? Probably the present value of that to you is 0, because you're probably not going to be around to receive it anyway. Lottery prizes are often not worth as much as claimed. What is the present value of a prize of $5 million that is to be received in 20 equal yearly installments with the first payment beginning today? Assume an interest rate of 7%. How do I do this?
You put in the calculator.
Calculator in begin, right? Okay, present value is what? 5 million. Present value. The n is 20, he says. Okay.
I don't remember the interest. 17.
Why 17?
I don't know.
7%.
You're
Question, if the present value is 5 million, why do we need to calculate anything? It's asking, what is the present value of a prize of $5 million?
Oh, because it's
divide the
distributed over
5 million
so
by
the 5
20.
million is the future value?
Nope.
Divide the 5 million by 20 and that's your payment.
You are so okay. Let's read it again. You have a prize of 5 million that will be paid out in 20 equal yearly installments. So you divide that by 20, and that is what? Your payments. Correct. So you don't know the present value. That's what you're trying to compute. You do know that you will receive these $5 million in 20 payments, which are $250,000 each. So that's your payment, and you want to find the present value. So the present value of this $5 million paid in 20 yearly installments is actually $2,833,000. So in a sense, the real value of this 5 million prize is $2,833,000. Why is that?
It's given over to you in the process of 20 years.
Because, yeah, some of those payments happen very far in the future, and since you have to wait for it, you would be able to generate those distant cash flows with less money today. Like, again, that's the idea of discounting. To receive those the last $250,000, which happen in 20 years, you would have to put in an account now at 8% or 10%, I think, is the interest rate, much less. Then just wait until you generate that future cash flow. So that will be the value of that future cash flow to you today, the present value of it. Think about the last payment. The last payment is $250,000 divided by 1 plus r to the power of 20. So you understand that this is small because it gets divided by 1 plus 1 to the power of 20. But do you understand the reasoning behind it, like the intuition behind it? To generate this $250,000 that you will receive in 20 years, you would need much less money today. You would need to set aside this amount so that after receiving interest for 20 years, it would grow into $250,000. That's why its present value is smaller. You would be able to generate that future cash flow with less money today. So by the time you actually receive those $250,000, okay. All right. Yeah. It's the same number we had there. Oh, yeah, sorry. I don't know, they inverted the question and the answer. You believe you will spend $40,000 a year for 20 years once you retire. In how many years will you afford to retire if interest rate is 6% and you can save $40,000 per year? So this is similar to the exercise we did earlier. You have some future that you are trying to, some future payments you want to receive, and you are trying to fund them by saving beforehand. So the first step is you need to figure out how much will you need to be able to generate $40,000 per year for 20 years. So the present value of this stream of payments to you. So take the calculator, put it back to end, and you have 6% is the interest rate, 20 is the number of years that you want to receive the payments, $40,000 is the payment you want to receive, and you want to compute the future value. So you need $458,000, 796, to be able to fund from there $40,000 withdrawals for 20 years. Yes?
Not future. You said future.
That's the present value.
You said future.
Did I?
Yeah.
That was wrong. Thank you. So this is the amount you need to be able to fund those withdrawals of $40,000 for 20 years. It's basically your pension to yourself. Now you need to figure out how long will it take for you to accumulate this amount if you are able to save $40,000 per year. So this, which is a present value, becomes a future value. Okay? And everything else is the same. 6 is still the interest rate. $40,000 is the payment, and you want to solve, wait, 0 is the present value, and you want to solve for n. It will take you 8.98 years if you can save $40,000 per year to generate this amount. So you will be able to retire in 9 years. See that the amount is the same, but of course it takes less to put together that present value, and then it supports more payments because you earn interest through the whole time. Both when in the phase when you are accumulating money and then when you start withdrawing money from the account, you still earn that 6% per year on the balance. Buy this new car for $30,000 cash, or with an appropriate down payment, pay $800 per month for 36 months at 5% interest. So this is what the salesperson offers. Assuming that the salesperson does not offer a free lunch, calculate the appropriate down payment. So either you pay 30% cash or some down payment, which we don't know and we're trying to calculate, and then $800 per month for 36 months at 5%. That the salesperson does not offer a free lunch, it means that this installment payments plan must not be cheaper than paying cash now. So how do I compute this down payment?
Figure out what $800. What's the present value?
What's very good. The first step is I want to figure out what is the present value of this payment plan. We have 36 months of $800 payments. 5% interest. I need to divide by 12 because this is monthly rates. And I can compute the present value. Very good. This is the present value of the payment plan. We know that since the salesperson does not offer a free lunch, meaning it cannot turn out to be more convenient than paying cash, it means that the present value of both the down payment and the payment plan must be equal to the value of the car. So $30,000 is the present value of the pay immediately option. You subtract the value that we just computed for the payment plan. Whatever is left is the amount that you need to be paying as a down payment. Yeah.
What did you say does not offer free lunch means?
Does not offer a free lunch means that it cannot turn out that by paying in installments you pay less than paying cash immediately. It's like it's not offering you something where you delay your payments and in the end you pay less. It's basically a cue to tell you the present value of the two options is really the same. In one case, you pay $30,000, so the present value of that is $30,000 because you pay it immediately. In the other case, I let you pay in installments, but it's not like you end up paying less. The discounted present value of the two options is the same. If interest rate is 6%, which of the following investments to prefer? All right, these you just need to compute them. First one is a payment of 40 a year for 20 years, starting in 1 year's time. That's really an ordinary annuity. B is a payment of a certain amount today. The present value of it is just the amount itself, because it happens today. There's no need to discount anything. A perpetuity of 30 a year, starting in 1 year's time. That's normal perpetuity payment divided by interest rate. Level perpetuity, the only type we saw. And a single payment of $500 at the end of year 3. You can compute it this way. You can also do 500 divided by 1 plus r to the third, which probably in this case is even faster. Compute them all and you compare them. And I think you want the highest? Yeah. So C, the perpetuity. Say it again?
Doesn't say highest.
Says which one of the following to prefer. You will prefer the one that has the highest present value because it's worth more, literally. You are by computing the present value of all of them, you bring their value to a common point time 0, like now, where you can directly compare which one is worth more. Yeah.
You gonna post the slides again?
Where? I can post them in the Excel module for Finance 3000. Yeah. Say it again?
We're gonna get a Blackboard notification when you do that?
Yeah. Don't you? Yeah, you do. I will also send them to all professors, and they might or might not post them on your session.
Where did you get the 420 and the option D? 420.
So 6% is the interest rate, 3 periods. You don't have payment. So computing this is the future value. That's $500 happening at time 3. And you want to find the present value. Now this is the same that you would get if you just discount it by 3 periods. 1.06 to the power of 3. So you want to divide 500 by that. Okay? You don't need to do it on the calculator with the time value of money function if it's just one discounting. But Miller's hardware plans on saving $42,000, $54,000, and $58,000 at the end of each year for the next 3 years. How much will the firm have saved at the end of the 3 years if it can earn 4.5% on its savings? What is this? Present value or future value problem? It's a future value, right? So this exercise is there because there are many ways to solve it. One way is to use the cash flow calculator. The cash flow calculator is a function in your calculator that lets you input repeating cash flow series. So when you use the PMT function in the time value of money calculator, you have the same payment happening all the time, the same one. here the cash flow payment, the cash flow calculator lets you say, for example, you have a 42,000, like in this case, payment that will happen once. Then you have, no, sorry, will happen once. Yeah, this one is, yeah. And I didn't enter it, thank you. I start being really baked. Okay, it will happen only once. Then you have a second one that is 54,000. Will also happen only once. And then a third one that is $58,000. Also will happen once. Okay. 4.5 is the interest rate. And compute. Say it again.
You put in the cash flows, then what you do?
Yeah.
How'd you get the I?
So you click NPV, and it asks you the interest rate to compute it. Now, did you ever see this before? No, not in class? Okay. Now, you can learn how to use it, but before, tell me how else could I have done it without the cash flow calculator?
Take 42,000 times 1 plus the rate, the second power, and then you do 54,000 times 1 plus the rate to the first power, and then you do 58,000 times 1 plus the rate to the 0 power.
Perfect. So you can always do that. You can always just discount or compound interest for each cash flow and sum them up. In this case, you had 3 cash flows happening at time, what, 1, 2, and 3? The first one was 54,000, no, 42. 42, 54, and 58. Okay? So this one doesn't really earn interest at all. Happens in year 3. And I'm trying to compute the future value at year 3. So I really only need to take care of this cash flow, which earns 1 plus R twice for 2 periods. And this one, which earns 1 plus R once. So in this case, to me, it's much easier to just compute 42,000 times 1 plus R squared plus 54,000 times 1 plus R plus 58,000. You sum them up, you compute the future value of each one of those cash flows at a common time, which is time equals 3. You sum up those future values and you, yeah.
Why do you leave CF0 blank and start at?
Because the first cash flow happens at time 1. I have nothing happening at time 0. The first saving is 42,000 at the end of the first year.
So if it was at the beginning of each year, you would have started at CF0?
If I had like saved something now, yeah.